In this video, we are going to define definite integrals and look at some examples. Definite integral of a function f over an integral ab is area under the curve between x equals a and x equals b. It is denoted as integral from a to b. So these a and b we call limits of integration. So a and b are called limits of integration. And f is the function, and dx means we are doing the integral with respect to x. So this basically means if we have function f whose graph is like that. So this is function f, and our x equals a is over here, and x equals b is over here. Then this area under the curve between a and b, so this area is given by that integral. And depending upon how f looks like, we may need to use different techniques to find this area. So for example, let's look at the integral from 1 to 2 of function 6x minus 6. Since we defined a definite integral as an area under the given function, graph of given function, let's first try to graph this function. So to graph this function, we can simply look at the intercepts. You see, we are trying to graph the function y equals 6x minus 6. So basically when x is 0, y would be 6 times 0 minus 6, so negative 6. So it should go through 0, negative 6. I'm going to say negative 6 is over here. So the graph will go through that point. And when y is 0, to get the x-intercept, we said y equals 0. So basically we solve 0 equals 6x minus 6. That will give us, if we add 6 to both sides, 6 equals 6x. Then you get x equals 1 if you divide both sides by 1. So the function will go through this point. I'm going to say this is 1. The graph of this function goes through those 2 points, so I can draw the graph. Since it's linear function, it's going to be a straight line, going like that. So 1 is over here, and I'm going to say 2 is somewhere over here. So now this integral is area under the graph of the function, which is this straight line between 1 and 2. So this area. This area over here. Since this graph is a straight line, it's quite easy to find this area. This area is a triangular region. It's a triangle. So we can simply find the area by using formula for area of a triangle, 1/2 base times height. The base is this length here, 2 minus 1, distance from 1 to 2, which is 1, times to get height. You can find y value over here because height will be this length. So for that, you can find the y value over here. We know the coordinates of that point will be 2, and you just plug in x equals 2 in the function. So 2 times 2 minus 6 is 6. So the y value is 6. So this height will be 6, and this base is 1. So this is the area of this triangle, which comes out to be 3. And this is the value of the integral. The value of this definite integral is 3, because area under the curve of this function, area under the graph of this function from x equals 1 to x equals 2 is 3. Let's look at the next example. So in this case, we have the same function, but different limit. So let's quickly draw the graph we had. Here we are looking at area from 0 to 3. In this case, we are looking at the graph of the function y equals 6x minus 6. When x is 0, y is -6. So the graph should go through that point. And we also found for this function that when y is 0, x will be 1. I can quickly solve that and show how we got that. So when y is 0, we have 6x minus 6. We can add 6 to both sides. 6 equals 6x. And then you can divide both sides by 6. You get x equals 1. So that would be the x-intercept. It should go through this point. I'm supposing 1 is over here. And then I'm also going to label 2 and 3. So 3 is over here. Okay, so the graph should look like this one, a straight line that goes through these 2 points. Like that. The problem wants us to find the definite integral of this function from 0 to 3. So we are looking at area under the graph of this function from 0 to 3. 3 is over here. So definitely it will include this area. Now, if you look at between 0 and 1, the area between the x-axis and the graph is this one. So we look at this area. But the thing is, if the area is under the x-axis, we consider that to be negative area. So if it's under the x-axis, this will be negative area. Okay, so let's quickly find out the area of these two triangular regions. So area of this one will be 1/2. I can say the base is this one. So 1/2, 1 times the height, which is 6. Area of this region is 3. And for this one, we have 1/2. So this length is 2. And we also need the height, which will be this length here. For that, we can find the coordinates of this point. 3, you just plug in x equals 3 in the given function. 3 times 6 minus 6 will come out to be 12. So the height is 12. This will give you 12. Right? So like we said earlier, this area 12 will be positive. And area 3 will be negative. So we do 12 minus 3, which is 9. So therefore, value of the integral is 9. Next example here. So here we are trying to find integral of the function y equals square root of 16 minus x squared from x equals 0 to 4. So the first thing is to try to draw the graph of this function. Now this one looks a little bit more complicated than the functions we looked at earlier. So you can try using a graphing calculator or some online tool. But if you want to draw by hand, let's square both sides. Let's try to rewrite this function by squaring both sides. So we get y squared equals 16 minus x squared. Now, if you add x squared to both sides, it will look like x squared plus y squared equals 16, which is simply a circle with radius 4, because we have 16, which is 4 squared, and center 0, 0. So we can draw the graph of such an object, a circle with radius 4 and center 0, 0. Let's say this is the circle we want. So we have 2 over here, 4, since the radius is 4. 4 over here, negative 4 here, and negative 4 here. Now, since the function is y equals square root of 16 minus x squared, we are actually looking at just the upper half of the circle. So we are just looking at this part of the circle, this upper half of the circle. So this is our function y equals square root of 16 minus x squared. And the integral we are looking at is from 0 to 4. The limits of integration are from 0 to 4. So we are looking at this area, just that area. So now we can find the area of this region. This region is simply a quarter of area of circle with radius 4. So this will be 1/4 pi. So you know the formula for radius of, so you know the formula for area of circle, pi r squared. So that means we have pi times 4 squared. Then this becomes 1/4 times 16 pi, which is 4 pi. So this is the value of the integral. Okay, this is the next example we have here. So this time we are not given what f is as an expression, but we are given its graph. Using the graph, we want to find the integral from 0 to 6 of function f. So this integral will simply be the area under the graph of f, which is given here. So let me try to denote that region. It will be all this region all the way up to 6. So we are looking at the region from 0 to 6. So we are trying to find the area of this region. So one way to do that is to try to divide this into several objects that we know. The first one, you can divide it into several ways. Maybe one of the ways to do that can be look at the region below this line. So this is a rectangle. This region is a rectangle with area, you see the length would be 6. So this whole length from 0 to 6, length is 6. And the height looks like is 4. So this height is 4, 6 times 4. So this area is 24. And we have a triangular region over here. So whose area will be 1/2 times base times height. The base of this triangle is this part, so which is of length 4 times height. So it looks like the height will be this length over here. So it looks like height is 2. So this comes out to be 4. So the area of this triangle is 4 and this whole rectangle is 24. So therefore, I can say this equals, so this integral equals 4 plus 24, which is 28. So this is the value of the integral. Next, we want to find integral from -4 to 4 of f of x, where f is given by this graph. It's the same graph as we just looked at, but the limits of integration are different. So in this case, we are looking at the region from -4 to 4, which is over here, under the graph of this function, which is given here. So we are looking at this region. So we're looking at this region. Again, we can try to divide this region into several parts so that we can find the area. We can divide this into different ways. Maybe we can look at one big triangle up to 2, like this one. And then we can look at another triangle up here. So this one, we have one huge triangle. Triangle 1. We have another triangle here, triangle 2. And then we have one small rectangle. Now all we need to do is find the area of these two triangles and this rectangle and add them up. So starting with this triangle 1, this area will be 1/2 times base times height. So let's figure out what the base and height are. The base of this triangle will be this length from -4 to 2, which is length 6. And the height is all the way up to here. So this will be the height of this triangle. So this is height 6 again. So the area of this triangle comes out to be 18. Okay, done with the first triangle. For the second triangle, again 1/2 times base times height. The base is this length, which is 2. And the height is this length over here, which is again 2. So this comes out to be 2. Done with the second triangle. Now the rectangle, the area of a rectangle is length times width. The length looks like is going to be 2. So this length over here. And the height or the width, I can call that to be this height here, which is 4. So 8. So now I have areas of the parts. I can just add them up to get the whole area under the graph of the function from -4 to 4, which will be the value of the definite integral. 18 plus 2 plus 8, which is 28. Okay, next we want to look at the definite integral of x squared from 1 to 2. Let's try to draw the graph of this region again. The graph of the function y equals x squared is a nice parabola. So I'm going to try to graph like that. And then we are looking at the area under the curve from 1 to 2. So the area we are looking at is this one. So this is the area we need to figure out. If we can find the area, then that will give us the value of the definite integral. So this is not one of the nice geometric figures like triangle or rectangle or trapezoid or square. So we cannot use any of those formulas to get this area. So this will be a little bit more complicated than the previous examples. So in order to find an area like this, we need to use a little bit more advanced tools for integrals, such as fundamental theorem of calculus, which we will do in our next video. Or we can also look at Riemann sums, the method of Riemann sums. So we will talk about these in our next videos.